This is Chapter 11 homework, problem number 71. A runner is approaching the start-finish line, and here's the bell signaling 1 lap to go. The bell emits a 352 Hertz tone, and the runner hears it at 359 Hertz. The question is asking how fast is the runner going. So first, it's important to recognize that we're dealing with the observer approaching a stationary source. So we use the equation f prime equals f times 1 plus the speed of the observer over the speed of the sound. And the question is asking us to solve for the speed of the observer. So by algebra, in the second line, we divide both sides by f, the frequency emitted. The next step would be to subtract 1 from both sides. And finally, multiply both sides by the speed of sound. So we have the speed of the observer is the speed of sound times f prime over f minus 1. When we plug in the numbers given in the problem, we get that the observer, the runner, is running at a speed of just a little under 2% of the speed of sound. So that comes out to 6.82 meters per second. Problem number 73. We have the source, in this case a goose, flying at 13 meters per second, and what's perceived is a frequency f prime of 257 Hertz. Part A is asking what was the emitted frequency. So first, in evaluating the problem, we recognize that the source of the sound is approaching a stationary observer. So this is the appropriate equation. And we are solving for the emitted frequency, meaning solving for f. So with algebra, we would want to, in order to solve for f, multiply both sides of the equation by this denominator. So now we have f equals f prime times 1 minus the speed of the source over the speed of the sound. Plugging in the numbers, we get an answer of 247.3 Hertz. Then part B is asking, what if the source is receding from us? The goose is flying away at 13 meters per second. What is the perceived frequency? So we recognize that the source is receding. So the appropriate equation is f prime equals f over 1 plus speed of the source over speed of sound. Plug in those values. And in this time, we learned in part A that the frequency emitted is 247.3 Hertz, so it's appropriate to plug it in for f, and we get a perceived frequency of 238.2 Hertz. Question number 75 involves a paratrooper jumping out of a helicopter, and 4 seconds later, calling back to the helicopter with an emitted frequency of 425 Hertz. Question is asking, what is the frequency perceived at the helicopter? So here we have a situation where the source of the sound is receding from a stationary observer. So here's the appropriate equation. Perceived frequency is frequency over 1 plus speed of the source over speed of the sound. But we have to figure out, what is the speed of the source? How fast is the paratrooper dropping? This goes back to kinematics. What is the speed of the source? Well, after 4 seconds of free fall, we can use our kinematic equation. The velocity is initial velocity, which is 0, plus acceleration, 9.8 meters per second squared times 4 seconds. So after 4 seconds of free fall, the paratrooper has a speed of 39.2 meters per second. So now we come back to this equation, and we say the perceived frequency is the emitted frequency, 425 Hertz, divided by 1 plus, and there's the paratrooper's speed, 39.2 meters per second, divided by the speed of sound. And so we get a perceived frequency at the helicopter of 381.4 Hertz. Number 79, we recognize that the observer is approaching a stationary sound source, and the question says that we are perceiving the frequency to be twice the emitted frequency. So here's a substitution we can make, that f prime equals 2f. If the observer is approaching the stationary sound source, here's the equation. F prime equals f times 1 plus speed of the observer over speed of sound. Now we'll make that substitution, that f prime is equal to 2f. So 2f equals f times 1 plus v of the observer over v of sound. Since f is a factor in both of these equations, we can divide both sides, in both sides of the equation, we can divide both sides of the equation by f, leaving us just with 2 equals 1 plus v over vf, vo over vs. It doesn't matter what the emitted frequency was. That exact number cancels out. Subtracting 1 from both sides of the equation gives us 1 equals vo over vs. So the ratio of speed of the observer over speed of sound is 1, meaning speed of the observer is equal to the speed of sound, and so we'll just take that to be 343 meters per second. In order to hear the frequency at twice its emitted frequency, you would have to be approaching the source at the speed of sound. Number 87. This is a level 3 problem. The emitted frequency is 52 kilohertz. The speed of the source, or the speed of the bat, is 7.50 meters per second. What we're dealing with is, first, there is the frequency as it's reflected off the wall. So the bat is moving towards the wall. It's emitting a frequency f. When the waves get to the wall, they are at a frequency f prime. We'll come back to that later. Then, the waves that are now at a frequency of f prime, they reflect back off the wall. The bat coming towards them will perceive them at a frequency of f double prime. So it's a two-part problem. First, we'll have to figure out what is f prime. What is the frequency of the waves as they hit the wall? So we recognize for this part that the source, or the bat, is approaching. Here's the equation. F prime equals f over 1 minus speed of the bat over speed of sound. We plug in the appropriate values. As long as I pay attention to the units, I can leave it in kilohertz. In the denominator, meters per second will divide out, leaving the denominator unitless, and it'll leave me with units of kilohertz. So the frequency at the wall, f prime, is 53.162 kilohertz. Now, let's apply that over here. Now we'll take that 53.162 kilohertz as being emitted. Actually, it's being reflected, but as pertains to the formulas that we've learned, we can take it as being emitted by the wall at 53.162 hertz. And now we're looking at a stationary source and a moving observer as the bat is moving towards the wall. So we'll find the frequency as the bat perceives it as being f double prime. We recognize now the observer is approaching a stationary source. Here's the appropriate equation. F double prime equals f prime times 1 plus speed of the bat over speed of sound. When we plug in the values, now we're using 53.162 kilohertz as the emitted frequency from the wall. And we get f double prime is 54.3 kilohertz. So the bat emitted a frequency of 52 kilohertz. And when the bat hears his own voice, or hears the sounds that he produced, he gets it back much higher at 54.3 kilohertz.